Hey everyone, this is my second video on gloss ceramics, and today I want to show you how you can make zero expansion materials from easy to find household gloss ceramics. And in essence, the method involves only one simple high temperature baking step. In my first video on gloss ceramics I demonstrated that materials with low thermal expansion can have some pretty cool features, like excellent thermal shock resistance. And the essence is that because they don't change shape under temperature gradients, they don't build up internal stress and therefore do not break. And this property makes them extremely suitable for cooktops and ovenware. But zero expansion is also useful in other applications, like astronomical optics. In order to get very good image quality from a telescope, you need to preserve the wavefront in the light to about a quarter of a wavelength or better. And this sets very high accuracy constraints on the shape of telescope mirror surfaces. With standard glasses, even the slightest temperature gradient can cause significant deformation of the mirror shape. So having a material that does not expand or contract with temperature is in this case a huge advantage. Let me quickly demonstrate this using a simple experiment. I've got two glass discs. One is made of ordinary soda lime glass and the other one is made of a low expansion material. Soda lime glass has a thermal expansion of 9 ppm per degree Celsius or Kelvin, and this means that if you have a length of 1 meter of this material, it will increase by 9 microns for every degree of temperature increase. Now 9 microns per meter of length doesn't sound like much. A human hair has a diameter of say 40 to 50 microns, which is about 5 times larger. So changes in length will be hard to see even for parts of 1 meter length. But we can easily visualize the deformations that take place under temperature gradients using a very basic form of interferometry. For this I will use a test glass made of Ceran with a diameter of 60 millimeters. Ceran is a type of glass ceramic that is known for its extremely low thermal expansion, so it will retain its shape. The test glass has at least one interface that is polished very flat, and this interface can be used as a planar reference surface to measure the flatness of other surfaces. If this test glass is placed on another very flat surface, like a second test glass, we observe straight and equally spaced fringes when we look at the reflections of the monochromatic light of a sodium lamp. We can change the wedge between the two and change the spacing or orientation a bit, but the fringes will be straight and equally spaced because both surfaces are very flat. This is what the interference fringes look like on an interface that is not really flat. It's actually unpolished window glass, and you observe that fringes are not straight and equally spaced, and in principle we could extract the surface shape of this piece of glass from the fringe pattern observed. Okay, what we'll do is take either of the two windows, which are polished fairly flat, and then place the test glass on top. And then this stack will be placed on a hot plate that has a temperature of 30 degrees Celsius, which is 15 degrees higher than the temperature in my workshop and the initial temperature of the glass plates. And during this procedure, we will observe the interference fringes using monochromatic light. Soda lime glass, which expands with increasing temperature, will change shape as shown here. Basically the surface under test will become somewhat concave, and we'll take a look at how much that is in the experiment. So this is the soda lime glass. Immediately you can observe how the straight fringes become ring shaped. This process stops at some point and reverses because the temperature gradient in the glass becomes smaller again as the heat is transported through the material. But as you can see, this reverse process is quite slow. The observed ring pattern can show us pretty accurately how much deformation is caused by the presence of the temperature gradient. Here I repositioned the test glass to center the fringes a bit more, which makes it easier to do the calculation. From center to edge there are an average of 29 ring-shaped fringes, and each ring represents a difference in surface shape of a half a wavelength between the interface under test and the test glass. This effectively means that within this area of only 60 mm in diameter we have a deformation of 14.5 wavelengths, and with the wavelength lambda being 589 nanometers, this is equivalent to 8.5 microns. So this means that the difference in distance between the two glass interfaces is 8.5 microns larger in the center than it is at the edge. And for such a small area, this is a pretty significant deformation. Now let's compare this to what happens to a window made of the zero expansion glass ceramic. Here we basically observe no noticeable change in shape during heating, which I think is pretty amazing. So the main point to take away here is that if we were to use these windows to make, for example, a reflective mirror, one will be very sensitive to temperature gradients, while the other will retain its original shape very well. As discussed in video 1, the manufacturing process of glass ceramics is pretty complicated. The material itself consists of a proprietary mixture of different metal oxides. On top of that, they are processed in a pretty complex high temperature process, so making a zero expansion glass ceramic from scratch is unfeasible unless of course your name is Nigel Brown. But as I said in the introduction, we're not going to do that. Instead, we'll take two relatively cheap and widely available glass ceramics named Robax and Ceran and make them perform quite a bit better at room temperature. I got this idea when experimenting with Robax. Just to see what would happen, I heated it to 1200 degrees Celsius for 15 minutes, which is far beyond its intended maximum use temperature of 700 degrees Celsius. And this resulted in the Robax to become completely white, like a little ceramic tile. Here on the left is the standard Robax, to the right a piece of the material that was overheated. It's quite different, so obviously the internal structure has changed quite a bit, but as turned out, the thermal expansion properties had also changed quite a bit. In the first video I talked in detail about how the linear coefficient of thermal expansion, CTE for short, can be measured. Basically what you do is measure changes in length of a piece of material as a function of the temperature of the piece. You can then calculate the CTE by first dividing the change in length delta L by the total length of the piece, and then divide this relative change in length by the corresponding change in temperature delta T. So if we plot the data for delta L over L as a function of temperature, the slope in the graph is equal to the value of the CTE. Now, since the changes in length are very small, you need a very accurate micrometer gauge, and for this I used one that has a resolution of 20 nanometers. It's actually a part of the incredible Ultra Spherotronic. Yeah, so here are the plots for the original Robax and for the thermally converted material. It's clear that the CTE value has changed significantly. Originally, the material has a CTE of around minus 0.6 ppm per degree Celsius for the temperature range indicated, which is from 15 to approximately 50 degrees Celsius. A negative value indicates that the original material contracts a bit with increasing temperature, which is of course somewhat unusual. But to my surprise, the converted material had a positive CTE of plus 0.5 ppm, which is still low. It's comparable to quartz, so you can still dip it in cold water when it's red hot and it won't break. However, that's not the point. You might see the potential that is hidden in these graphs. What if we don't heat Robax all the way to 1200 degrees Celsius, but to a somewhat lower temperature in between? Would we then maybe be able to make something that has a zero CTE? To make the measurement setup more accurate, I had to make a vital change to it. So in a CTE measurement, I clamp a warm sample between a rod of low expansion clear ceram and a micrometer gauge, and then measure the change in length of a sample as a function of its temperature while it's cooling down. What I had expected was that the stainless steel pin of the micrometer gauge would not heat up because of the sapphire ball on top of it. Basically, I expected the ball, it being a ceramic, to act sort of as a thermal barrier. But what do you know? Sapphire has a thermal conductivity that is 3 times higher than that of stainless steel. So if you place the sample in the setup, what happens is that the pin actually heats up slightly and then also starts to cool down during the measurement. And this added a systematic error of around plus 0.1 ppm per degree Celsius to the measurement values presented in the previous video. It's not a huge error, but I felt I needed to mention it. Also, to prevent this from happening here, I added a little cap with a net expansion of 0 that can be placed on top of the ceramic bowl. It's made of a combination of 2 low expansion materials that have coefficients of opposite sign. And this cap can act as a thermal barrier between sample and gauge pin and prevent the issue in the upcoming measurements. With this problem out of the way, I'll now discuss the experiments done on both Robax and Ceran. Now, of course, I didn't know whether the idea would even work or what value to use for the temperature, so I decided to do a set of conversion tests between 900 and 1100 degrees Celsius in steps of 50 degrees Celsius. And for each conversion I would measure the resulting CTE. For the conversions I used a dental kiln. The inside diameter is pretty small, around 90 millimeters, so I had to cut strips of 80 millimeters length in order to make them fit inside. A nice feature of this kiln is that you can program firing profiles that are very reproducible, which is essential for the upcoming experiments. I bought this thing about 12 years ago, second-hand for 200 euros. It was not like a huge investment or anything. And another great feature is that the kiln itself is inside a small vacuum chamber, so the conversions can be performed under vacuum. Unfortunately, I had a problem with the vacuum pump. Yeah, I'm afraid the pump is jammed. Sorry? We've got a pump jam.
Pump jam! While your feet are stumping. Yo, and the pump is pumping. Look ahead, the crowd is jumping. Make my pump.
Well, good thing we don't need vacuum anyway, because all samples were just fired under atmospheric conditions. And I used the temperature profile as shown here. The samples were preheated to 500 degrees Celsius for 3 minutes. Then I ramp up in 20 minutes to the actual conversion temperature, where the value is kept constant for 10 minutes. And then the sample is cooled down relatively quickly to below 750 degrees Celsius in say 3 minutes, and then gradually to room temperature. If we inspect the samples visually after they have cooled down, we can see how an increasing baking temperature gradually changes the appearance of the samples. Robax becomes more and more opaque at higher temperatures. Ceran has a reddish dye in it, so it's not highly transparent to begin with, but above 1000 degrees Celsius it changes color to purple and also becomes more opaque. So let's take a look at the coefficient of thermal expansion found for the converted materials, starting with Robax. For conversions of up to 950 degrees Celsius there are no changes in the value of the CTE. However, at a conversion temperature of 1000 degrees Celsius, the CTE has suddenly changed in sign. Also, the value is almost 5 times lower in the absolute sense than that of the original material. And then at 1050 and 1100 degrees Celsius, the CTE values increased further to about plus 0.3 ppm. So what we can do is take the CTE values from this graph and then plot them as a function of baking temperature, which is shown in this figure. And a zero value should in principle be found somewhere around 990 degrees Celsius, but it's hard to pinpoint because of the limited set of data points. So what we'll do now is add a few readings at temperatures between 970 and 1000 degrees Celsius to get more data points in this area. These are the results of the CTE measurements for 970, 985, 994 and 1000 degrees Celsius. I also blew up the scale on the y-axis a bit. So if we put a linear fit through each dataset, we get the following CTE values for these conversion temperatures. And the one that attracts the attention is of course this one, the conversion at 994 degrees Celsius. It resulted in a CTE value of minus 0.058 ppm. Now you might be tempted to say, still a bit negative, so not zero. And why not use 995 degrees Celsius as the conversion temperature? Well, let's take a closer look at the data. That is definitely not a straight line. It's actually curved, and when we look where this curve has a zero derivative, so a zero CTE, it turns out to be somewhere between 20 and 25 degrees Celsius. So for use around room temperature, this specific material would pretty much be ideal. Here I've plotted the 994 degrees Celsius curve again, but blown up in the scale in the y direction quite a bit and added arrow bars to this plot. The vertical error is determined by the resolution at which the relative changes in length can be measured for samples of 80 millimeters long. The error in the temperature reading is approximately plus or minus 1 degree Celsius, so errors are pretty substantial, but there is unmistakably a curvature in this plot going from positive to negative CTE, and at exactly 24 degrees Celsius we find a value that is pretty much 0. Of course, the whole point of having a low CTE is that we want this in a temperature range that is as large as possible and not just at 24 degrees Celsius. But it's clear that here we basically need to compromise. So the next thing I did was take the data in this figure and calculate the CTE between the neighboring points. I then plotted these individual values for the CTE as a function of temperature, like shown here. Because we're on the edge of the measurement resolution, the result is a messy plot, but I hope the essence of what I'm trying to show you here is clear. If we now fit a curve through these data, we find how CTE varies with temperature. Well, let's say that the material is going to be used in a temperature range between 20 and 30 degrees Celsius. Looking at the fitted curve, this means that in that range the CTE does not vary more than, say, plus or minus 0.05 ppm per degree Celsius. I agree, this is a small temperature range to work with, but I think it's still a very nice result. To put the expansion of this material into perspective, if you have a bar of a full 1 meter long, it will change length by no more than 50 nanometers per degree Celsius when kept within this range. That is approximately 1/1000th of the diameter of a human hair, or 10% of a single wavelength of visible light. By now you probably want to know what this material looks like exactly, and it's actually this one here. And not coincidentally, it's also the same material that I showed you in the first experiment, where we looked at deformation on a hot plate. It's not highly transparent, but that's not essential if you want to make first surface reflective optics, and it turns out that you can polish it to a very nice surface finish. The same thing is actually true for converted Ceran, which I will talk about in a minute. So even though these materials are not designed for it, they can still be used to make reflective, zero expansion optical parts. Okay, let's do a quick evaluation. So baking the Robax at 994 degrees Celsius reduced the CTE value of the original Robax by a factor of 10 in the same temperature interval. But how does this compare to commercial glass ceramics that are tailored for extremely low expansion? Well, the value I specified here is actually lower than that of shot class 2 0-dur. However, this is somewhat unfair because CTE values of 0-dur are specified within a temperature range of 0 to 50 degrees Celsius, which is quite a bit larger than our 10 degrees C interval. And if you go to the best 0-dur available, it's clear that there's still quite a lot of work to be done in order to get to the same level of performance. Okay, so these were the results for Robax. As a summary, I plotted the CTE values at 24 degrees Celsius as a function of the baking or conversion temperature again. It shows that for a baking time of 10 minutes, a value of 994 degrees Celsius is the optimal value. Now, of course, we can do the same experiments for Ceran, the material used in cooktops, and this is where it gets really interesting. I will not go through the whole set of experiments, but quickly take you to the highlights. The CTE versus temperature scan shows that the optimal conversion temperature is a bit lower for Ceran, around 960 degrees Celsius. And if you look at the original graphs that were used to create this plot, we again get curves instead of straight lines. Now, as you can see, all these curves start at delta L over L is 0, and that is because in these plots the lowest temperature data point is always used as the 0 reference for any changes in length. However, the interesting aspect is that you can change the temperature where 0 CTE is found by tweaking the baking temperature. So if you intend to use the material in the range between, say, 25 and 50 degrees Celsius, you might want to bake it at 965 degrees Celsius. If you intend to use it at 20 degrees Celsius, you're better off with a baking temperature of 961 degrees Celsius. So what this figure shows is that you can tune the temperature where 0 expansion is found to a very specific value. Unfortunately, the value for the CTE I found for Ceran is a bit higher than the value found for Robax. If you bake Ceran at 961 degrees Celsius, I find that the CTE is plus or minus 0.1 ppm per degree Celsius in a temperature range of 16 to 28 degrees Celsius, which is not as low as the value for Robax. But if you compare this to soda lime glass, it's still about 90 times lower. And yes, if you do the 30 degrees hot plate tests on converted Ceran, you can observe that it also does not deform at all. Now, before you take the temperature values presented in this video for granted, 2 remarks. First, the oven I used is not calibrated, so baking temperatures will probably not be very exact. And this means that if you want to try these conversions yourself, you need to do a few test measurements first in order to get really good results. And second, the optimal conversion temperature can vary between Ceran batches. Here are 2 plots for Ceran taken from 2 different cooktops using an identical baking profile. And what you observe is that the temperature at which 0 CTE is found is not the same. So that's it for this video. I hope you enjoyed the ride, maybe even got some inspiration from it. Anyway, thanks for watching.